All right, good morning, good afternoon, everyone. So today I'll be discussing some of my ongoing work for the submission at the SAM 21 conference at Las Vegas on July 26th. So this presentation will be discussing, the topic of the presentation will be Sandy Toolbox, and this is a framework for dynamic malware analysis and model development. So as a presentation overview, I'll be discussing some of the problem. Next will be the methodology and how we proceed going forward. Thirdly, the results and future work. Finally, our conclusions. So as a general overview, this presentation is focused on the Sandy Toolbox, and this is within the research of something called malware honeypots. So what malware honeypots are is that they're honeypots where practitioners and researchers want to understand how malware works. So we need a place where we can execute it in a safe manner, and we do so in a controlled environment, usually in some sort of virtualized environment. The problem with this is that many malware, in order to implement some form of anti-emulation behavior, have become VM aware, which means that they either can complicate the reverse engineering process by having while executing a virtual environment can run forever, or they can fail to execute their payload altogether and just lay dormant or remove themselves. So this is all ways in which they make it burdensome to make it so that it's difficult to understand exactly how the malware works and to make our lives as researchers more difficult. So when malware is executed, it's executed in a malware honeypot, and then in some way the malware honeypot implements some form of logging, so it tracks exactly what's going on, and then the researcher or practitioner is the one that interprets that information. So the thing is, malware honeypots, honeypots in general, just come in all shapes and sizes. Some malware honeypots just focus on SSH communication, SQL and other forms of databases, Internet of Things devices, and just virtualizing those and seeing how, let's just say, malware propagates. And finally, we have malware honeypots, which is going to be the focus of this presentation. Other popularized forms of cloud-based honeypots, like VirusTotal, which is owned by Microsoft, use the Cuckoo sandbox in their backend. Cuckoo just being a very popularized form of honeypot that is used in research. And Cuckoo is known for collecting dynamic form of behavior. So these tools facilitate the collection of static behavior as opposed to dynamic behavior as opposed to static. Dynamic being that the malware is actually executed in order to see exactly what it's doing within the host operating system. So once that information is collected from dynamic behavior, it takes subject matter experts to make use of that information for downstream analysis and other downstream tasks. So that could be model development or just creating signatures for static base analysis and classification. So here we look at the problem statement. So as it stands, current sandbox and honeypots are standalone products. That is to say, you just download them, you collect the logged information, and then you make use of them however you wish. And they're standalone products in that way. The issue is that these products require subject matter experts to make or create signatures or to integrate whatever heuristics are found into, let's just say, an intrusion detection system. For example, just creating signatures, you can see in the idea of a static analysis, it could be saying what sort of assortment of opcodes or bytecodes is characteristic of this malware or this malware family. Okay, let's create a signature within our antivirus system that looks for that. And finally, heuristics can just be, okay, if we're looking at network traffic, what sort of anomalous form of network traffic tells us that there's a denial system happening, or that there's communication with an outside command and control system. So that can take place in the form of a heuristic. But for our question is, how can we integrate, let's just say, the processing and model development into a single toolbox for researchers and make it readily usable and available? So just this graphic at the bottom just shows how we can collect the raw data, and that could be executed in a virtualized environment or some other form of analysis that can just look at a portable executable and extract all those static features. So whatever form that raw data comes, we can categorize it in static features or dynamic, and then we can pass it into some sort of heuristic or hybridization model. Hybridization just meaning we can combine the static and dynamic features in order to create sort of a feature vector. We can pass it into a machine learning model, and finally we have some form of classification. We're classifying malicious versus benign, or this malware family from this other type of malware family, or this type of malware functionality, like a rootkit versus another type of form, just like the ransomware. So for our work and our contribution, we're focused on the creation of our own sandbox. So we're doing this in a dynamic form because that's how we see the future of analysis going towards for various reasons, which I mentioned later on. And that's because we want to track the behavior of malware through a sandbox environment. And we coined this sandbox environment called Sandy, hence Sandy the Toolbox. So in our implementation, we use Process Monitor, which is a sysinternals tool provided by Microsoft. And what it does is, it's used for debugging, it's used for it's used for malware analysis, it's used for your own type of code snippets for debugging. But what it does is it records all event activity, including the file system, so what's being installed on the hard disk, registry, so activity in the registry, file and thread system activity, so what processes are responding and with what threads. Another sort of tools that help simulate real network. This is all part of the anti-emulation behavior that comes with certain malware. They can tell whether or not they're in a virtual environment by, for example, looking at what ports are open. So iNetSim and DNS spoof will spoof a DNS or produce and simulate network activity in order to fool malware, a certain percentage of the malware in order to fool it. And the other thing it can be used for is to track anti-emulation behavior. And this will be explained later on, that regardless if a malware can test for an emulation environment or a virtualized environment, the steps that it takes in order to do that can be classified in a way. So this bottom graphic here just shows as a very bird's eye view on exactly how this is done. This is all very sort of standard when it comes to virtualized environments. So the toolbox, I said, does more than just those standalone products. It actually implements the processing and the model development in one. And how it's implemented in its current version is that we have modules that can handle the importing of the raw data from the toolbox, or from the feature data collection steps of the toolbox. It can process it, it can graph it, and it can model the dynamic features. The other thing it can do, which is very important when you're executing malware, is that you need to trace the spawn behavior of malicious processes and their corresponding event behavior. This is very important because malware is not executed on its own. It's executed in an operating system with other processes running. So however it's running, the background processes or the benignware that's running is as important to know than the malware, because nothing about malware is executed on its own, right? It's always in the context of other things. And the question is, within that context, is there an impression that it makes, or is its behavior in such a way we can tell exactly what's going on or what it's going to do and stop its behavior before it infects the host operating system. The other thing that in this current version the toolbox does not do is it doesn't include executions from downloaded binaries. So if you have a particular malware that is able to reach out to some other external repository, so it acts as a downloader, and then it downloads some form of additional malicious code, and then it executes that code. In its current version, the Sandy Toolbox cannot trace that. So what it only does is it traces the malware that's executed initially. At these bottom illustrations here, on the left, we just have a depiction showing how the import module passes information to the PP or pre-processing module, and then you can graph it or model it in order to develop your own forms of classification. And the figure on the right just demonstrates how you know exactly what's being executed to start with, and that you can look at the process identifier and the parent process identifier labels in order to trace exactly what is being spawned from that initial process. So in this way, this is why it can't track things that are downloaded from a downloader, for example, because it needs a target label, and then it just looks at what's spawned from there. But ideally, how this would work is that before a downloader is able to do what it does, that we can stop in its tracks. So as a case study, as a proof of concept of this work, we traced the execution of the Trojan Emotet malware. And this was actually a banking Trojan that up until January 2021 was responsible for a lot of damage to infrastructure and so on and so forth. It was actually responsible also for a huge botnet for hire service. And for our work, what is shown here is just a quick view of what the Sandy Toolbox is able to do. The graph on the left just demonstrates all the dynamically linked libraries that are spawned, not just from malware, but just from all the operating system and benignware that's running in the background. And this is just to demonstrate that malware is a small proportion of exactly what's going on, and it's always, again, in the context of everything going on in the operating system. So it's a needle in the haystack, and that's why it's so difficult for us as practitioners to find that needle in the haystack. In the figure on the left, the only other thing to note is that the color of the nodes, which are different shades of blue, the lighter it is, sort of the earlier it was executed, or earlier it was imported, and the darker it is, the later it was. So there's sort of a time sequence to this figure. And the table on the right just goes to show that if you're looking at registry, file system, network, parent process, and thread activity, and profile related to the kernel, what percentage of total activity is responsible for baseline? Baseline being operating system, new processes. If you were to, in this case, start Adobe Acrobat Reader or remote desktop, what percentage of those event activities belong, of the total event activity, which proportion of them belong to registry, file system, network, process, profile. So this is just to show that in a baseline, registry makes up the most part when it comes to activity. When new processes are executed, of course, a larger proportion of them become file system as an image is taken and loaded into memory, and files are created on the file system all the time. But back when it's when you have the baseline and those processes, it's sort of on the very right, baseline and new processes, what you find is that returns back to sort of baseline. So this is just to demonstrate that if you're looking for a needle in the haystack, maybe registry is not the best place. In our case, actually, we found it worked very well, but this is just to demonstrate, for demonstrative purposes, what you can come to expect. And the total number of event activities is at the bottom row. So for our again, for our case study, as we know, malicious activity represents a small proportion of total activity. So in our case, if we look at the benign activity within the full execution of the Emotet malware, in total you had about 146,000 benign event activities. Of all those, well, not of all those, but separately, 480 were just responsible for the malicious activity of the Emotet malware, the bulk of which were responsible for registry and file system, and there was no communication via networking at that point. So when we're looking at proportion, malicious activity only represents a small fraction, a third of a percentage of that event activity. So it's not very. So again, it comes back to that needle in the haystack, and we need to find some techniques that can extract those useful features, or we need to find features in which malicious activity in particular there's evidence of in the activity. So just a few points. Process and thread activity had a slightly larger proportion as a percentage when files are executed. So that's just interesting to note that 2% of all activity was responsible from the process and thread. And that's just because with benignware, everything that's running is running as background processes, right? So the creation of new processes and threads, maybe not threads in the case of malicious, but new processes occur when malware is executed, which makes sense to us. And that's just to note that benign activity includes some background process as well, but the events are dominated by operating systems. So in the previous slide, when I was mentioning the Adobe Acrobat Reader, or with remote desktop, the number of events is dwarfed relative to what's going on in the Windows operating system, right? And it's not enough just to remove those. I mean, you could, but the idea is that you want to know exactly what's going on and something to be representative of a real environment. And in a real environment, you're collecting process activity from all sorts of sources. So finally, this case study, we just wanted to give you a quick look at if you're looking at registry, process and thread, and file system activity, for the sake of simplicity, we just focus on those three. And we were looking at all the function evocations from Windows API. What is the proportion of those, right? So in the case of the registry, what is going on in the registry with the emotet malware in terms of proportion relative to that of background processes or the benignware, which is the remote desktop in the Adobe Acrobat Reader. Oh, sorry, the Adobe Acrobat Reader in the remote desktop. So one thing quickly to note is that a large proportion of registry open key versus registry set info key, opening and set info. This is just to demonstrate that if you look at registry set info key, which isn't exactly the name of the Windows API call, usually those are sort of just those are just labels that are lookups. There's actually a proper function name for that. Emotet malware had a larger proportion of its activity where it was calling that Windows API, and a small proportion of registry enumerate key or enumerate value, right? So again, this is just to look at if you had a weak label for something that's slightly more likely malicious or not. This can give us a hint. Again, so always think of these as hints and not end all forms of definitive proof of anything. Finally, when we're talking about process and thread activity, it sort of makes sense that even with background processes, they're spawning. Oh, sorry, with benignware, they're creating processes, they're creating threads. But malware in particular, at least in this case with the emotet malware, had a lower proportion of thread create. So malware doesn't have the motivation to start processes and to be particularly effective in its use of resources, and it doesn't need to create multiple threads because it's not doing anything that's long lasting. So that's just a hint that you can tell just from looking at, again, these proportions of total activity. Of course, largely the total activity is dominated by just loading images, right? So loading files into memory or on. And finally, we can look at file system. So again, file system is just looking at the hard disk, what's being created, what's being closed. There's a high rate of close file for malware compared to that of benignware and background processes. So this sort of makes sense to us. If you have any form of background process or benignware, it has the idea that it has the motivation that it wants to stay persistent on hard disk, that is, as opposed to malware will want to create files and then typically cover their tracks by deleting what has been done. So we see a high proportion of closed file relative to that of benignware. And just as a quick overview of current work, we looked at just very briefly some of those Windows APIs and the proportions of it, proportions of one relative to others. But really, these function calls, what really matters is that they're called in the context of other calls, right? Because that's what tells you the true behavior of something. It doesn't tell you anything if close file is used or it's not, but used in the context of other things can actually tell you quite a bit. So in a sort of what I want to call like a sister project or sister paper to this work was this paper that we also published this year that looked at actually the stack traces. So every single form event has to make communications with the Windows API, and then it goes down from a high level to a low level to the kernel, where it makes kernel calls in order to make use of the Windows operating system resources. So we could look at all the function calls and say that, okay, if malicious or benignware uses this API call in the context of others, is it more likely malicious or not? Again, so it's more looking at context. And we looked at the whole stack trace as well to detect malicious behavior. So the thing is, even with anti-emulation, which has been known to occur in something like 70% of malware currently, we can still investigate the behavior of malware even when it checks for virtual environments. So whatever it does relative to checking in the registry or making other checks for virtualized environments, that in and of itself is malicious behavior, and we can track that by looking at these stack traces. So this example we found actually did quite well when we tested it, so the best results were actually found for file system and registry activity, so the stack traces belonging to those types of events, with 94% plus F1 score when we tested it on the execution and the events of 9 malicious families. So finally, bringing it back to the sandbox environment that we coined Sandy, it collects dynamic process behavior, and we showed that through some preliminary results of we showed this by just touching upon some preliminary results of the graphing module, looking at some of the API calls, and just looking very surface level of their proportions. So a quick case study looking at Emotet malware demonstrated that even just as a weak form of evidence, Windows API calls are different for malware versus background processes, and that when coupled to downstream tasks, in the case of the stack trace, we use natural language processing applications, malicious activity is evident and can be classified. So this is just a quick summary, introduction to the Sandy Toolbox and some of the other things that we can do with it. So with that, I thank you for watching, and if you have any questions, please send those to my email as the main correspondence for this paper, and I thank everybody for watching.